A very warm to one and all. I'm Professor M.S. Patil, Department of Mechanical Engineering, Maratha Vidya Prasarak Samajas, Karmavir Advocate Baburao Ganpatrao Thakre College of Engineering. Today, in this video presentation, we are going to study about the levers. The learning objectives of this session are, first we will see what are levers, what are the different types of levers, and how to design the levers. So first, starting with what are levers. Levers are nothing but they are the mechanical devices in the form of rigid bar pivoted about the fulcrum to multiply or transfer the force. In a very simple language, we can say that a lever is nothing but which minimizes the effort of a person in order to lift a certain amount of load. Or we can say that heavy loads can be lifted with the help of minimum amount of effort. The most common example of a lever is a spanner. A spanner can be used to tighten a nut or a bolt. So a spanner acts as a lever. So with the help of minimum effort, we can apply maximum amount of force. We can see a simple construction of a lever. A lever is nothing but it is what we can say a construction which has three pins. One is a fulcrum pin, one is a load pin, and another one is a effort pin. It is just simple like a seesaw, right? On one end, it is effort which we are applying in order to lift the load. The distance of the point where the effort is applied from the fulcrum. Fulcrum is nothing but it's a hinge. So the distance of the effort from this fulcrum is called as effort arm, and we are going to denote that effort arm by L1, and the distance where the force or the load is applied from the center of the fulcrum, it is called as load arm L2. So this is a simple type of a lever which are commonly used. So F is the force produced by the lever and P is the effort required to produce that force. The force is often called as load, and the perpendicular distance of the line of action of any force from the fulcrum is called as the arm of the lever. So this will be effort arm and this will be load arm. So if we are taking moment about this fulcrum, then what we will get, force into perpendicular distance, that is P into L1 should be equal to F into L2. So we can get P into L1 is equal to F into L2, or rewriting the things, F upon P will be equal to L1 upon L2. Now this particular ratio, F upon P, load upon effort, it is called as mechanical advantage, and this distance L1 upon L2 is called as leverage. We will see it in this slide. So mechanical advantage is nothing but the ratio of load to effort, and what is leverage? The ratio of effort arm to the load arm, that is distance L1 upon L2. So from the previous expression, we can say that mechanical advantage is equal to the leverage. For the what we can say effective utilization of the lever, mechanical advantage as well as leverage should be always greater than 1. That means the length of the effort arm should be greater than the length of the load arm. So we can first study what are the different types of levers. So as earlier explained, right, there are three relative positions. One is of the effort, second one is of the load, and third one is of the fulcrum. Then depending on the relative positions of this effort point, load point, and fulcrum, we can classify lever into three main categories. This is the first type of lever, right, where the fulcrum is in between the load and the effort. We can see over here, this is fulcrum, this is effort, and this is force or load that is being applied. This is effort arm L1. This is load arm L2. Effort arm is generally greater than the load arm, or in some cases it may be equal to the load arm also. Such type of levers we are finding in the application of the rocker arm for the overhead walls of internal combustion engines when we are operating the input and out exhaust valve, right? For operating those valves, such type of levers are used. Also, we find the application of such type of levers in bell crank levers used in railway signaling systems, or the best example is of the lever of a hand pump. These are the most commonly and efficient levers which are used in mechanical purposes. Second type of lever is the lever in which fulcrum is on one side, load is in between, and effort at the other end. We can see the example over here, fulcrum at one end, force, and the effort at the other end. Now, such type of levers we find in the operation of safety valves of the boiler. The boiler valves are located over here, right? When the pressure inside the boiler, when it exceeds a certain limit, then this force will be more than the effort applied, and automatically it will open, and excess amount of steam will be relieved, and the pressure inside the boiler will reduce. Then automatically P will close the valve. So such type of levers we find in the application of lever loaded safety valves mounted on the boilers for operating the valves. The third type of lever are the levers in which effort is located in between fulcrum and the load. You can see effort is in between fulcrum and the load. More amount of effort is required to lift less amount of load, and therefore we are not preferring such type of levers in mechanical applications. We are not generally using them, but we can say picking fork is an example of this type of lever. So these are the three main types of levers which are used in mechanical engineering applications. Now, talking about design of levers. In design of levers, there are three main parts. First part is about the force analysis. Second part is related to determination of cross section of the lever. And the third part is related to calculating dimensions of the fulcrum pin, or either load pin or the effort pin. So talking about the force analysis, either F or P will be known, either load or effort will be known, L1, L2 are known. We can determine the unknown from this particular equation, which is calculated using taking moment about the fulcrum. Once P, F, L1 and L2 are calculated, then we can go for calculating the reaction at the fulcrum, because fulcrum is a hinge point, and where there is a hinge or a support, there is a reaction, and that reaction has to be calculated first. So talking about first type of lever, right? Fulcrum is in between effort and load. This is load, this is effort, this is fulcrum. Direction of reaction will be up. Summation of F of Y, vertical forces, should be equal to 0. We can get upward forces is equal to downward forces, and from there we will get R is equal to P plus F. If we are talking about second type of lever, then R plus P is equal to F, or R is equal to F minus P. In this way, reaction can be calculated. And in third type of lever, or any other lever, a bell crank lever or angular lever, right, where the arms are inclined, right, we can calculate reaction by using cosine rule. We can calculate reaction as under root of F square plus P square minus 2 FP cos of theta. If we are talking about a specific lever, for example, bell crank lever, where the angle is 90 degree, then cos 90 is 0. Then in that case, R will be equal to under root of F square plus P square only. So we have calculated the reactions at the fulcrum for different types of levers, right? Once the reactions are known, we can go for the designing of fulcrum pin or the design of cross section of the lever. Then design of lever arm. So when we are talking about the design of a lever arm, it's a specific type of lever. This is load arm, this is load point, this is effort point, this is effort arm, this is load arm, this is the fulcrum. At fulcrum, there is a pin of diameter D1. There is a boss of diameter twice D1, right? The weakest section will be where the slot is there, and therefore taking moment at this slot, what we will get, P into this much distance, bending moment. So P into L1 minus D1. So P into L1 minus D1 will be the bending moment. So considering the bending criteria and using flexural formula, we can determine the dimension. Now the cross section of the lever, here in this case it is shown as rectangular one. It can be elliptical cross section, it can be I section also. So depending on the type of cross section, we can find out the different parameters. If it is a rectangular cross section, then this will be width, this will be depth. I can be calculated as BD cube by 12. Y is the distance of extreme fiber from neutral axis. This is neutral axis. Extreme fiber is here, so D by 2. And generally D is taken as twice B. If it is not mentioned, you can consider D is equal to twice B. It can be mentioned as 3B, 4B also, right? So we can put those values. If it is elliptical cross section with a minor axis B and major axis A, then moment of inertia can be calculated as pi BA cube upon 64. Y is distance of extreme fiber from neutral axis A by 2. And the relation between A and B can be given, or otherwise it can be taken as A is equal to twice B. So using flexural formula, what is flexural formula? Sigma B is equal to MB into Y upon I. In the previous slide, we have seen how to calculate MB. MB is nothing but P L1 minus D1, right? Y, if it is a rectangular section, it can be taken as D by 2, I pi by BD cube by 12. Or if it is a elliptical cross section, we can put those values. If it is a I section, we can put those values and calculate the unknown parameters in the design, either B or D, either A or B, or if it is I section, then the thickness of flange, width of flange can be calculated. Now the third part is the design of the fulcrum pin. This is the fulcrum pin. Now generally the fulcrum pin is located inside a brass bush, right? This is the inside diameter of pin, that is D1. If we consider either a bush of 3 or 4 or 5 mm, right, then this will be the enlarged diameter, and this will be the diameter of the boss, that will be twice D1. Now the pin and the bush, right, they are having relative motion between them, and therefore the design criteria will be bearing pressure. So talking about the fulcrum pin is subjected to reaction R. The forces acting on the boss of the lever and the pin are equal and opposite, right? The dimension of the pin, which diameter D1 and length L1 in the lever boss, are determined by bearing consideration, because there is relative motion. And once we have calculated the dimensions using bearing consideration, we will check them from shear consideration. There is relative motion between the pin and the boss of the lever, and bearing pressure becomes the design criteria, right? Therefore, bearing pressure P is equal to force upon area. Projected area will be D1 into L1, where D1 is the diameter of pin inside the bush and L1 is the length of the bush. So using this, okay, here again there are two unknowns, L1 and D1. Therefore certain relation should be mentioned. Many a times L1 is taken equal to D1, or it is usually the ratio L1 upon D1 is usually taken from 1 to 2, right? Then the outside diameter can be calculated as twice D1. The phosphor bronze bush, usually of 3 mm thick, is fitted inside to reduce the friction. Then the permissible bearing pressure for a phosphor bronze bush is taken in between 5 to 10 Newton per mm square, unless and until it is specified. And then a lubricant is also provided between the pin and the bush to reduce the friction. So using the relation, you can calculate D1 and L1, which relation bearing pressure is equal to force upon area, right? See, one thing must be noted over here. if reaction on the fulcrum pin is either less than the load or effort, then we have to design those pins, right? Because higher load has to be considered for calculating the diameter of the pins. And for interchangeability purpose, if we have designed a pin at load point of higher diameter, same pin can be used for fulcrum, and same pin can be used for effort also. So you have to consider the higher value of force over here. But as we are talking now about the fulcrum pin, then we will be taking the load which is acting on the fulcrum pin, that is the reaction on the fulcrum pin. So using the reaction of bearing pressure P is equal to R upon D1 L1. D1 L1 relation can be up to 1 to 2. We can calculate the values of either D1 and L1. And then finally checking it for double shear. The shear stress induced is force upon area. Double shear, therefore 2 into pi by 4 into D1 square. If the value of shear stress is within the limits less than the permissible values, permissible value can be calculated as 0.5 SYT upon factor of safety. If it is found to be less than the permissible value, then we can say that the fulcrum pin is safe in shear. And in this way, we can calculate all the dimensions which are related to the cross section of the lever, diameter, dimensions of the pin, and calculation of the forces. That's now that's okay for now. In the next lecture, we will see the numericals, specific numericals involving the applications of the levers. Good day for now. Thank you for listening very patiently. Thank you. Thank you very much.